Okay, so welcome to lecture 7 of week 4. So today what we'll be talking about is the so-called Flory Huggins theory and the chi parameter. So that's what we will reach. And what we are discussing basically about is when will a polymer mix in a solvent? Be it so suppose it's a good solvent, and so what is the criteria? Of course it's energetics, but it is also entropy of mixing. So when will the polymer mix in a good solvent, and it depends upon the so-called chi parameter. And when will it be a bad solvent? So and basically there will be a certain range of chi parameter when it will be the so-called bad solvent, and sometimes it will be a good solvent. So when a polymer is in a good solvent, it is basically is going to spread out. Excluded volume interactions are going to play a role, and the radius of gyration, as we have discussed in the last class, will go as the n, where n is the number of monomers in a chain to the power 3 by 5. We are of course considering dilute polymers, not much interaction. Whereas if the solvent is such that it's a bad solvent, so that the monomers want to be in, uh, it's favorable, it's free energetically favorable for a monomer to be in uh, close proximity with each other rather than be in contact with the solvent. And then the polymer will be in a collapsed state. It will basically compactify. It won't like to spread out. And then it's called the globule state. And in that case, the radius of gyration, which is an estimate of the size of the polymer chain, goes as n to the power 1 by 3. So where does this scaling law come from? So it's basically saying that suppose the polymer is completely compact. So all the volume, the size of the polymer is such that there is no solution or solvent molecules within the polymer. They all have been um, uh, thrown out of the volume where the polymer where the monomers are. And in that case, the 4 pi r cube, r being the estimate of the radius of gyration size of the polymer, 4 pi by 3 r cube is into volume, which is volume of a monomer, is equal to n, which is the total number of monomers in the chain. And from here you get r goes as 1 by n to the power 1/3. Okay, so the discussion in terms of a good solvent, bad solvent is going to be slightly different from the previous class, where we were just calculating the excluded volume parameter of a monomer, right, in terms of the interaction energies, because we are going to also consider entropy of mixing. Okay, so it's the free energetics which is going to decide it, and not energetics alone. So it's the free energy thing which is going to be going to calculate. We're going to also discuss osmotic pressure and so on and so forth, but let's. So, if there's a free energy for mixing, suppose some solute is mixing in a solvent, the free energy would have two contributions. It would have entropy of mixing, and also one has to consider the energetics of mixing, right? Whether a monomer or any solute, in our case, since it's a polymer physics course, whether a monomer wants to be, it's energetically favorable to be in contact with the solvent, or is it energetically favorable to be in contact with itself, right? So that's the energetics, but over and above that we have to consider entropy of mixing. And entropy of mixing, we shall be considering three cases to begin with, just to start out the discussion, which will be basically this lecture. It's the entropy of mixing of two atomistic solvents. So we'll first calculate that, but then suppose, so basically the volume taken by each solvent and the solute particles is the same, V0, let's assume, right? So the size of the uh, constituent particles is the same. So the mixing of two atomistic solvents, that's what we mean by that. The other case is that the entropy of mixing of a long polymer chain, right, is a connected object. and that is getting basically mixed in a atomistic solvent. So basically, each monomer will has the approximately the same volume as the atomistic solvent, but the we are more interested to calculate the entropy of mixing of an entire polymer chain in a solvent. And the last case is entropy of mixing of a polymer chain with monomers in a chain in a solution of another polymer chain, which is also liquid, but it consists of polymer chain. It's not an atomistic solvent, but with say NB molecules per polymer chain. So these are the three different cases. Our entire discussion will be mean field description. So we'll be not considering correlations. We'll be making quick estimates and say, okay, the effect of one monomer or one particle with another is the average effect of its neighbors. So it's a mean field description, and we'll be using simplifying assumptions. Okay. So with this background and with this basically introduction of what we're going to discuss this week, or what we're supposed to discuss in week 4, I go ahead. So first, let's discuss in today's this lecture the entropy of mixing of two atomistic solvents, where the constituent molecules are basically of the same volume. So first of all, what we do is we discretize space in a lattice. So suppose the entire volume of where the solute and the solvent is, the entire x, y, and z direction, the entire volume, the phase space, if you like. Well, we are talking only of configuration space XYZ, not momentum. So the phase space is discretized into a lattice, and the point is, notice. I mean, suppose you took a smaller a degree of the volume, the configuration space, right? It won't matter, because we can measure only free energy differences and gradients. So that's what we can measure. So if you take smaller volumes for each constituent, it is going to finally cancel out. Okay. And the first thing we are going to discuss is entropy. So initially we're not going to discuss energy cost or interactions. We're going to introduce it, of course, when we discuss free energy. And the question we are asking is, if there are A particles, and these are solute particles. This is airness. I should be writing it as solute. A is solute particles, and B is the solvent molecules. Suppose it's water molecules, and A is much less than B, right? What are the total ways to arrange A and B particles? So you would see that the number of A molecules are considerably less than B. Each A is surrounded by B particles. And what are the total ways to arrange A and B particles in a lattice with, suppose, n uh, n lattice points? Okay. And that is essentially, if you think about it, is just Na, the number of A particles, plus number of B particles, factorial. uh, and we are assuming that A particles are identical and B particles are all identical. So if you exchange the position of all the A particles, suppose you exchange, take this particle here and this particle here back, then you won't be able to make any difference. You won't be able to see any difference. So that's what it means by identical particles. And the number of ways to arrange in A plus B particles on a lattice, where Na plus Nb equal to n, the total number of lattice sites, is this formula, right? And you can see that very easily. Now suppose this entire lattice site was empty, then you could put the first particle in n ways, where n is the total number of lattice points, and you could put the second particle in n minus 1 ways, and then third particle in n minus 2 ways, and so on and so forth. So the total number of ways you can put any n particles is n factorial ways, right? But if all of n of these particles were absolutely identical, okay, so suppose there was no A or B, there was only B, and all there were n B particles, then you could basically interchange all of these n particles and you would reach the same state. So the total number of ways you could have n indistinguishable particles in a lattice of with n sides is n factorial divided by n factorial, because you can interchange any of them, which is 1. But if you have A particles and P particles, then the total number of ways you can arrange N particles is Na plus Nb factorial. But then you could interchange all the Na particles and you could interchange all the Nb particles. As a consequence, the total number of ways to arrange is this formula, right? I mean, those who have had statistical mechanics, I'm sure they would have any problem. But just I discuss this in a greater detail because there might be third year students as well. Okay, so that's why I spent some time to discuss this. Okay, but yeah, so the assumptions that we are going to finally use is that there's a dilute solution. Uh, in this expression, we don't have any assumption of dilute solution, but later we are going to invoke dilute solution, right? So we are going to invoke a dilute solution in a later part of the class. So the number of A particles is much less than number of B particles. Suppose B particles is water, H2O. Okay, and the BB interactions are incorporated only through the chemical potential. However, if you add an A particle in a lattice of B particle, in a lattice full of B particles. So basically, A particle is surrounded by B particles in all different sides, I mean, all different directions. Then the energy cost on introducing the A particle is epsilon. Okay, this is just the energy cost, not the free energy cost. This is just the energy cost. We will consider no AA interaction initially. So you always assume that any A particle is surrounded by B particles only. So no AA particles are considered, which comes within this dilute approximation. We'll of course correct for it, but it's in the next class. And you say that when the box is full of B molecules, the number of ways to fill the lattice is n factorial by nb factorial, which is equal to 1, because n equal to nb when the box has only B molecules, no solute particles, right? But on addition of Na solute particles in a lattice which has n sites, you basically can now arrange it in many more different ways, much more than one. And then the entropy of mixing. And what was entropy? It is the number of microstates that you can access, different microstates that you can access with the same energy. So that's the entropy of mixing is Kb log the number of microstates. We have not considered energy here. We'll consider energy in the next step. Right now, this is the entropy of mixing. And basically, next, now you see ln of, I mean, this is the basically the statistical, this is formula comes from statistical mechanics. Entropy is basically Kb log number of microstates. And if you have Na plus Nb factorial, we are going to use the Stirling's approximation. Hopefully, you have seen Stirling's approximation before in this course. I mean, fourth year students, of course, have seen it, but I'm just talking about the third year students. And that is ln of n factorial when n is very large, can be written as n ln n minus n, right? We're not going to go through the derivation. We didn't go to the derivation in a statistical physics course, but it can be found in the books. But we are going to use this expression in this course to derive our results, which means that uh, okay. But before I go ahead, let me discuss a bit about what is the chemical potential, especially of a pure solvent. Now, suppose this was your lattice with n sides and there are B molecules. This entire lattice is full of B molecules. I've not written it, but I've written here full of B molecules, suppose, right? And now you add an extra B molecule in the solvent, in the bulk of the solvent, right? So I've increased the volume a bit and I've added a B molecule. And basically, the chemical potential is the change in the Gibbs free energy when you add this extra B particle. And chemical potential is the amount of Gibbs free energy per particle on introducing a new particle. And I would like to remind you, and this comes from statistical physics. If for the third year students, you have to wait till you go through a statistical physics course. The chemical potential equal to G, which is the Gibbs free energy per particle, and it comes from StatMech. What was Gibbs free energy? It was U minus Ts. U is the internal energy minus temperature, entropy, plus PV, pressure and volume, right? And if mu, the chemical potential, so you're introducing an extra particle, the chemical potential is basically Gibbs free energy per particle, which is U by N minus T S by N plus V P V by N. V, S, U, they are extrinsic quantities. Okay. Now, if you have a solvent and a solute, right? Suppose it's not all pure solvent, right? Then basically, then and suppose you already have n solute particles and some solvent particles, some and NB solvent particles, then the chemical potential of the solute, okay, is the Gibbs free energy change on adding an extra solute particle. So the chemical potential of A, which is the solute, is the Gibbs free energy of total solvent plus solute, where there are ns plus one solute particles, because you're introducing a solute particle, minus the Gibbs free energy of ns solute particles in the lattice of which has n sides, right? And basically, when you add one more chemical, when you add more particle, you have to keep pressure the same, right? Because Gibbs free energy is defined in terms of pressure and number of particles and temperature, of course, right? So this is the Gibbs free energy. So we are going to use this relation after this. So this was just an interlude to discuss chemical, just to give you a physical picture of what is the chemical potential. But now going from here to calculating the entropy of mixing, so that we are now using the Stirling approximation. So Kb equal to n log n, so Na plus Nb log Na plus Nb minus Na plus Nb, which is n log n minus n, where n is now Na plus Nb. So you should just refer. So basically, I'm just calculating this, breaking up each of the factorial terms, and that comes. So basically, this minus this, now in the denominator it comes with a minus sign, and this minus becomes a plus. So this is what you get, and you do a bit more of algebra, right? Because these terms cancel, Na plus Nb minus, and this cancels. And if you do this algebra, then the entropy of mixing is minus kb. Basically, I've taken out the kb. I'm just na log na upon na plus nb, which is total n particles, number of n sites in the lattice, nb into ln nb na plus nb, right? This is the expression, and this is the most general expression, right, where we have not assumed whether it's a dilute solution or not. And this relation we will use also in the part 2 of this lecture. Okay, so we'll be also using this will be the starting point of point 2, part 2 of the lecture. But for dilute solutions, what we are going to say that Na is much less than Nb. So in the denominator, we are going to neglect Na compared to Nb. Hence, this becomes Na by Nb plus Nb into, now see, there's the Nb here. We are adding an Na here and subtracting an Na here. Then we are writing it as 1 minus Na upon Na plus Nb, and again neglecting Na with respect to Nb. And this is the kind, so basically this approximation is used here to get this as well as here, right? And this is the uh, term that you get. And why is this important? So basically what you get is uh, then the entropy of mixing is minus kb nw, right? It is the number of water molecules, if you like, b molecules. So basically nb, this I've written here as water molecules. So it's minus kb log 1 minus this, and na into na by nw, right? Now here we are going to use one more approximation, ln of 1 minus epsilon. And why we are using this, you'll just get to know. We are going to derive Van 't Hoff's law. And this can be written simply as minus epsilon, right? So if you invoke this, then this law, this ln 1 minus Na by Nw becomes minus Na by Nw. Simplifying, we get entropy of mixing is minus kb Na ln of, if you like, concentration Na by Nw minus Na. Okay, and this is the entropy of mixing, right? Now the Gibbs free energy. So this was only entropy of mixing, but Gibbs free energy will also have energetic terms. So Gibbs free energy of introducing Na particles in a lattice of N equal to Na plus Nb sites, so B and water basically, is Nw, the number of water molecules, into the chemical potential if there was purely water molecules, right? So the chemical potential of water molecules in sites. And then these are the correcting terms. If there are A molecules, if there are A solute particles, it is surrounded by solvent particles, and the energy cost is epsilon. That's why plus this epsilon into Na. Here we are assuming dilute solutions, ignoring AA interactions, right? And minus T entropy of mixing. See, the pressure and the volume and so on and so forth is already incorporated here. So these are just the correction terms on introducing Na particles. You're assuming pressure is not changing, volume is not changing, and just replacing um, Nb particles by Na particles, and this is the corresponding cost, right? And basically, if A particles were not there, then you would have N into mu 0 W to be the Gibbs free energy. But anyway, here we have A particles, and NW is then less than N, right? So basically, then this can be, so all that I have done is written down, substituted S mix from here, and written this expression here, right? And then what we get is the Gibbs free energy is NW, number of water particles into chemical potential of the water particles, plus energy cost of A particles, plus KBT into Na log Na by NW. It's basically the volume fraction, if you like, minus Na. Right? This is the kind of expression you get for the entropy of mixing term. Na log Na by NW minus Na. This is, of course, easy to calculate. Now, the chemical potential of the solute is del G del Na, right? You add one more solute particle, what is the Gibbs free energy change? And that's why del G del Na. And if you take the derivatives, right? So if you take del Na, then from here you get -1. When you take the when you take the basically derivative of this quantity into Na, you get a +1, and so this is basically the answer, that epsilon. So now this is chemical potential that gives free energy for adding one more particle. So you first give an energy cost of epsilon, plus due to mixing, the contribution from the entropy of mixing is kBt into log Na by Nw, and this is 0. Now this can be written as Na by V box and Nw by V box, right? So the chemical potential of solute is energy cost epsilon plus kBt ln Ca, concentration of A particles. So basically Na by V box into Nw by V box. Now, of course, yeah, so this is the basically the what you get as the chemical potential. So if you know the concentration essentially, then you get your chemical potential for solute. So Ca by Cw, right? Now, now, so this I have written down for A particles. Now the chemical potential for the water molecule, right? So that has to be calculated when there is a solute present. When there is a solute present, we had written down the Gibbs free energy. Is actually we have to put in correction terms because you have now solute, right? So that would be del G del Nw, the solute particle, or W is equal to B. So W for water would be del G del N number of solvent particles, water particles, and again you take this expression, but now take the derivative del del Nw with respect to Nw. Nw is setting here and it is setting here, and once you do the derivatives, what you get is the chemical potential of pure water when there was no solvent, no solute, minus Ns by Nw, the fraction of solute particles. Okay, so the change in the chemical potential due to the presence of solute particles is the chemical potential of the pure solvent minus the fraction of solute particles that you have in the lattice or in the volume into kBt, right? So basically what you have, and then when there is a solute particle, is that the chemical potential actually decreases, right? Because it comes with a minus sign. Okay, So, as a consequence, now if you take a box which has A and B particles, or A and water particles, if you like, there is purely sorry, there is A plus water particles, and it is put in contact with the chamber B, which has B particles only, or water particles only, right? So that its chemical potential is mu W for water, 0 for it's pure, right? There is no solute particles here. Whereas here it is chemical potential W without the 0, because there are solute particles also here. So the chemical potential for water here is mu W, here it is mu W 0, right? And we already calculated that this is less than this value. By how much? By this amount. And suppose they're separated by a semi-permeable membrane, right? If they're separated by a semi-permeable membrane, then you know that basically if initially both they were at the same pressure, so this chemical potential and this chemical potential are calculated at the same pressure, suppose P1, then basically water molecules will move from this chamber to this chamber, right? As a consequence, the pressure in this chamber will go up. So water will flow from the B only chamber, right? B is water, this is the solvent. So water will flow from the B only chamber to the A plus B chamber to make the chemical potential of water equal. So two things will be so basically this system and this system will be in equilibrium only when the chemical potential of each of the species is equal, right? In this case water. But you know that the chemical potential of water, if both are in pressure P1 and both chambers are on the same pressure, is less by this amount. So water molecules will go in here, change the pressure, and change the chemical potential, right? And this difference in pressure, okay, because there are more water molecules here, that is the so-called osmotic pressure, right? So what I want to say is that osmotic pressure is a consequence of the entropy difference between the two sides, right? Basically, the origin was the presence of the solvent molecules, right? And all that we wrote down was basically, well, the chemical potential uh, for A molecules is epsilon plus kBt. This, but if you look at the chemical potential of water molecules, this chemical potential of water is less than the chemical potential here. So water molecules is going from this chamber to that chamber to increase the pressure of this chamber. As a consequence, you have osmotic pressure, and this is coming essentially from entropic terms. So osmotic pressure is a consequence of the entropy difference between the two sides. If you look at the derivation, and okay, you could ask why doesn't uh, basically water move from A plus B to the B chamber, B only chamber, the water only chamber, because if it does that, then the chemical potential difference will increase further. But you will get equilibrium only, right? Only if the two chemical potential becomes equal. Why will it decrease? Because the number of water molecules here is going to go, if it comes to this side, this NW will decrease. So this chemical potential will decrease further. The potential difference will increase further, right? But if molecules go from here to here, then this NW, which was here, will become NW star, right? And the chemical potential will become equal. So, sorry. So water has to move from B to A plus B chamber to get the to get the two chemical potentials of water equal on both sides of the chamber. And if volume of A plus B chamber remains fixed, this is the solute plus solvent chamber, if that remains fixed, then pressure will rise because more molecules of water are going in, and basically the pressure will rise from P1 to P2. And if it goes from P1 to P2, then the chemical potential also will change in the A plus B side from mu P1. So this is chemical potential of water from which was at pressure P1. And remember, gives free energy, chemical potential, these are all functions of pressure, temperature, and number of particles. So it will change from chemical potential P1 to chemical potential at P2, which will be at some different value. The pressure in A plus B chamber will rise. As I have said, chemical potential will change. Of water will go from chemical potential at P1 to chemical potential at P2, which will have a different value. And this will go on continuing till till the chemical potential of the pure case water in the B only case on the right side at pressure P1 becomes equal to the chemical potential, right, at pressure P2. This had N0 molecules of B only. This has Na molecules plus Nw star. I add a star because more water molecules have gone into that chamber, which has A plus B in solution. And in equilibrium, the chemical potential for each component, in this case the water, has to be the same. So this will keep on changing till this condition is satisfied. But what is this quantity? At pressure P2, as we found out from this formula, it is the chemical potential of water, pure water, 0 at pressure P2 minus fraction, I mean, Ns by N star W into kBT, right? It is, I'm just using this, except now NW0, it is for P2 because I am writing this. So I'm writing a correction term for this I'm writing in terms of NW0 P2 minus this is the chemical potential of pure water but at pressure P2. So this quantity, chemical potential of pure water at pressure P1, equal to chemical potential of pure water at pressure P2 minus this quantity, right? This becomes equal to this, and this can be written as this. Furthermore, using simple Taylor expansion, the chemical potential of pure water at pressure P2, temperature T, and N0, because the entire lattice is filled with N0 water particles, B particles if you like, equal to the chemical potential of pure water at pressure P1, N0 particles, equal to del mu del P calculated at P1 T N0 into P2 minus P1. From thermodynamics or statistical physics, whatever, this quantity is the volume per molecule. So I compare this relation, which is a Taylor expansion, with this relation, which I have rewritten here. And what do you get? You get P2 minus, so basically this term is here and this term is here. And then comparing this on this terms, you get P2 minus P1 equal to Ns by V. V is volume per molecule to N star W into kBT. So if temperature increases, the pressure difference increases. So whenever some quantity increases proportionally with temperature, it means it's an entropic effect, because as you increase temperature, the entropic contribution becomes more. P2 was the pressure on the left hand side, solution side. P1 was the pressure at the pure side, and this difference in pressure is proportional to kBT, an entropic effect. It depends upon the solvent particles, number of solvent particles, or rather the ratio of solvent particles, and the N star W is the number of water particles, right? And of course, the star has been written because water has come in from the B only chamber and changed the number of B molecules. We writing NW or NB here, but now I'm replaced by a star and I've marked it by a different color. And now this quantity, so N star V is basically, since you're considering a dilute solution, is basically the volume of a box. And then what you have is P2 minus P1, okay, is the number of the concentration of solute particles into kBT. As you increase kBT, this pressure is increasing, shows itself. Entropic effect, right? So basically the approximation is used is N star V equal to V box. Just to get an idea of numbers, okay, this was a bit of algebraic manipulations, but at the end of it we see that the pressure difference will increase as the number of solute particles increases. More interestingly, it will increase even with the same number of solute particles if you increase kBT, I mean the temperature. Shows that it's an entropic effect. But how much does this contribute? Is it weak? Is it strong? What does weak and strong mean? Right? These are just numbers, and you'll get out a number. But we want to have numbers with which we can relate with, or systems which we can relate with, because I mean, coming from physicists, put in some solution in some water, and you'll get some osmotic pressure. It doesn't mean anything. I mean, it should mean, but I'm trying to give you a sense of numbers. And something which we are very familiar with is inside the cell of the human, whatever organism or the human body, the characteristic concentration of inorganic ions is basically around 10 to 100 millimolars, right? 0.01 to point molar solution. Box of the V box of a cell is 10 micron cube, and this entire discussion is basically page 266 of Physical Biology of the Cell from Rob Phillips. By the way, he's a physicist, Caltech physicist, but he has moved from doing condensed matter physics to look using physics tools to understand biological system. So physical biology of the cell is basically to take the biological system and you use bending of beams and elasticity theory, entropy theory, statistical physics, currents, resistance, so on and so forth, to figure out the properties of living systems. Anyway, so this discussion is from there. So within the cell, how much is the osmotic pressure? What in terms of real terms? It basically, if you put in the numbers, right, from 10 to 100 millimolars, it corresponds to a pressure difference inside and outside of the cell of around 10 to 100 atmospheres. Right, that's high. 1 atmosphere is a number which you can relate with, right? And inside the cell there is much more. So in a normal cell, I mean, without any regulatory mechanism, if you put a cell inside and drop it in pure water, because outside the cell also there are various ions, but if you just take a cell and put it in pure water, then the pressure difference would be around 10 atmospheres. It would burst. But of course, inside the body, there are other ions outside the cell also. And moreover, a cell has various complex mechanisms so that the cell does not burst when put in pure water. And for some cells which don't have the mechanism, they do burst, right? And here I quickly show basically how we get 10 to 100 atmospheres, 10 millimolars, 10 to 100 millimolars is basically, I mean, 100 millimolars is zero point 0.1 moles is so many molecules, 6.02 into 10 to the power 23 uh, ions per right in 18 cc of water. That's what it means. Then you say that okay, so much volume of water contains so many ions, so how much would one volume of a cell, how many ions would it contain? And then you put in P2 minus P1 equal to, you put this number into kBt and number of particles by Vpox, and you'll see that you get around 100 atmosphere. And if you have 10 millimolars, you will get 10 times less. This is an order of magnitude calculation. Okay. So we discussed basically osmotic pressure today. We shall continue this discussion in the next class to figure out free energy of mixing and the high parameter. When will polymer molecule basically dissolve in a solvent, and then when it won't.